Far beyond the orbit of distant planets, deep space stretches in every direction. It is not completely empty, though it often seems that way. Thin clouds of hydrogen drift for light years without meeting much resistance. A few atoms may occupy an entire cubic meter. In this quiet setting, particles move slowly, guided by gravity and faint radiation from long-vanished stars. Between galaxies, darkness is not a solid wall but a gentle absence of light. Tiny fluctuations in the cosmic microwave background pass unnoticed by anything nearby. These faint signals are remnants of the early universe, now cooled to just a few degrees above absolute zero. They drift evenly through space, carrying information without sound or urgency. In the outer regions beyond familiar constellations, stars appear as steady points. Their light travels for millions or billions of years before reaching open space. Photons cross vast distances without touching anything at all. Most will never meet a surface. They continue forward, spreading thinner as space itself expands at a gradual and measurable rate. Dark matter moves quietly through this expanse. It does not shine or absorb light, yet its gravity shapes the paths of galaxies. Scientists infer its presence by observing how stars orbit. In deep space, its influence is subtle but persistent. Structures form slowly over immense spans of time, guided by forces that operate without sound. Interstellar space within a galaxy feels sparse and calm. Gas and dust exist in low densities, far below anything found on Earth. Occasionally, gravity gathers this material into molecular clouds. Over millions of years, these clouds may form new stars. Most of the time, however, the particles drift quietly, cooled by radiation into a gentle balance. Cosmic rays pass through deep space as streams of high-energy particles. They originate from supernova remnants and active galactic nuclei. Traveling near the speed of light, they rarely collide with anything. When they do, they transfer small amounts of energy. Otherwise, they continue onward, crossing silent distances without leaving a visible trace. The temperature of deep space averages around 2.7 Kelvin. This faint warmth comes from the cosmic microwave background. It is uniform in every direction with small variations. Objects placed in this environment gradually radiate heat away. Without a nearby star, they cool toward the steady background, reaching a quiet thermal equilibrium. Gravity operates across unimaginable distances. Even in emptiness, every mass attracts every other mass. The pull is weak but never zero. Over billions of years, it shapes the large-scale structure of the universe. Galaxies gather in clusters and filaments, separated by enormous voids that contain only a few scattered particles. In the far reaches beyond galaxy clusters, vast cosmic voids expand slowly. These regions contain very few galaxies and almost no stars. The density of matter there is lower than the cosmic average. Light passing through a void experiences little interference. It moves steadily, tracing paths defined only by the curvature of space. Black holes rest quietly at the centers of many galaxies. Their gravity influences nearby stars and gas. Far from their event horizons, space feels ordinary. Light bends slightly as it passes. Over long timescales, black holes may slowly evaporate through Hawking radiation. The process is gradual and measured in spans longer than the current age of the universe. Neutrinos drift through deep space in vast numbers. They interact only through the weak nuclear force and gravity. Most pass through planets and stars without effect. Generated in nuclear reactions within stars and in the early universe, they travel almost undisturbed. Their presence is subtle, a quiet background of motion through the cosmos. Magnetic fields thread through galaxies and extend into intergalactic space. They are weak compared to those on Earth, yet they guide charged particles. These fields arise from moving plasma and ancient cosmic processes. In deep space, their structure is diffuse and extended. Charged particles spiral gently along invisible lines. Time in deep space has no preferred rhythm. Without nearby activity, changes occur slowly. Stars evolve over millions or billions of years. Galaxies merge in patient sequences. Expansion continues at a steady rate. Observers would see motion only after long intervals, as distances grow slightly larger with each passing epoch. Radiation from distant quasars crosses enormous stretches of space. As it travels, its wavelength lengthens due to cosmic expansion. This redshift carries information about how fast space is growing. The light grows fainter and cooler. By the time it reaches remote regions, it blends softly into the broader cosmic background. Microscopic dust grains float between stars. They form from elements created in stellar cores and supernovae. These grains can absorb and scatter light. In deep space, their distribution is thin. Over time, gravity may draw them into new clouds. Most remain suspended, turning slowly and reflecting faint starlight. The large-scale structure of the universe resembles a web. Galaxies trace long filaments around vast empty regions. Computer simulations show how gravity shapes this pattern over time. In deep space, these filaments appear as distant gatherings of light. Between them lie expanses where only sparse particles drift in quiet isolation. Even in apparent emptiness, quantum fields remain active. Virtual particles briefly appear and vanish within tiny intervals. This activity does not disturb the calm of deep space in any noticeable way. It reflects the underlying nature of reality at small scales. On larger scales, space continues to appear still and open. Signals sent from spacecraft gradually fade as they travel outward. Radio waves spread in all directions, weakening with distance. Eventually, they become indistinguishable from background noise. In deep space, information disperses gently. The waves continue onward, expanding across regions that contain almost nothing to absorb them. Over immense timescales, stars exhaust their nuclear fuel. Some become white dwarfs that cool slowly. Others leave behind neutron stars or black holes. In deep space, these remnants drift quietly within their galaxies. They emit little light compared to their earlier stages, contributing to a calmer and dimmer cosmic environment. As the universe continues to expand, galaxies move farther apart. The average density of matter decreases. Regions between structures grow wider and more isolated. Light from distant galaxies may eventually stretch beyond detectability. Deep space becomes even more diffuse, marked by steady expansion and the persistent, faint glow of the cosmic background. Deep within a massive star, nuclear fusion steadily converts hydrogen into helium. As hydrogen becomes scarce, the core contracts under gravity. Temperature rises gradually. Helium begins to fuse into heavier elements such as carbon and oxygen. Each stage lasts a shorter time than the one before. The star adjusts quietly, balancing pressure from fusion against the inward pull of its own mass. When helium in the core is depleted, the star continues fusing heavier elements. Carbon can become neon, neon becomes oxygen, and oxygen becomes silicon. Each reaction requires higher temperatures. The structure of the star forms layered shells, like an onion. Fusion proceeds calmly in these shells, creating energy that flows outward as light and heat. Eventually, silicon fusion produces iron in the core. Iron is different from lighter elements. Fusing iron does not release energy. Instead, it requires energy. As iron accumulates, the core no longer generates enough pressure to support itself. Gravity begins to dominate. The core grows denser, with atoms packed more closely together. As the iron core increases in mass, electrons are forced into protons. This process forms neutrons and releases neutrinos. The pressure from electron motion declines. Without that support, the core contracts further. Densities approach those found in atomic nuclei. The change happens rapidly in physical terms, yet follows predictable physical laws. When the core reaches a critical mass, it collapses inward. The infall occurs in a fraction of a second. Matter moves toward the center at significant fractions of the speed of light. Neutrinos stream outward in vast numbers. The collapse halts when nuclear forces and neutron pressure resist further compression. The sudden halt of the core's collapse sends a shock wave outward. This wave travels through the outer layers of the star. Neutrinos transfer part of their energy to the surrounding matter. The outer layers are pushed away from the core. The star's material begins to expand into space. This outward movement disperses elements created during the star's lifetime. Carbon, oxygen, silicon, and heavier elements move into the surrounding interstellar medium. The expanding cloud cools gradually. Over time, it mixes with existing gas and dust. These materials may later form new stars and planets. If the remaining core has a mass below a certain limit, it becomes a neutron star. In this state, matter is composed mostly of neutrons. The star's radius may be only about 20 kilometers. Yet its mass can exceed that of the Sun. Its gravity is strong, though stable in structure. Neutron stars often rotate rapidly. Conservation of angular momentum increases their spin as the core contracts. Some emit beams of radiation from their magnetic poles. When these beams sweep past Earth, they are observed as pulsars. The rotation slows gradually over long periods as energy is emitted into space. If the collapsing core exceeds the mass that neutron pressure can support, it continues to contract. A black hole may form. Its boundary, called the event horizon, marks the region from which light cannot escape. Outside this boundary, space behaves according to general relativity, with predictable curvature. During the star's final stages, neutrino emission carries away a large fraction of the energy released in collapse. These particles interact weakly with matter. Most pass through the outer layers without obstruction. Their brief burst can be detected by sensitive instruments on Earth, offering information about the internal process. The expanding remnant of the star forms a supernova remnant. Gas and dust spread outward at thousands of kilometers per second. Over centuries, the material slows as it interacts with surrounding interstellar gas. Shock fronts heat the gas, causing it to glow softly in different wavelengths. Heavy elements such as gold and uranium are formed during the explosion. Rapid neutron capture processes occur in the intense environment. These elements become part of the expanding cloud. Over cosmic time, they are incorporated into new planetary systems, contributing to the chemical diversity of the universe. Massive stars live shorter lives than smaller stars. Their high mass leads to higher core temperatures and faster fusion rates. A star with many times the Sun's mass may live only a few million years. Its evolution proceeds efficiently, guided by gravity and nuclear physics. Before collapse, a massive star often expands into a red supergiant. Its outer layers grow cooler and larger. The surface may extend beyond the orbit of nearby planets. Despite its size, the core remains compact and active, fusing progressively heavier elements in concentric shells. The loss of outer layers can also occur through strong stellar winds. Massive stars emit steady flows of particles during their lifetimes. These winds carry away mass gradually. By the time of collapse, the star may have shed a significant fraction of its original material into surrounding space. Binary companions can influence the death of massive stars. If two stars orbit closely, mass may transfer from one to the other. This exchange alters their evolution. The timing and nature of the final collapse can change, depending on how much mass remains in the core. After the explosion, the remnant core continues to cool. A neutron star radiates residual heat and magnetic energy. Over millions of years, its temperature declines. the surrounding supernova remnant expands and becomes less dense. Eventually, it blends into the general interstellar medium. In some cases, the collapse may produce jets of material along the star's rotational axis. These jets can move at high speeds and emit intense radiation. When aligned with Earth, they are observed as gamma-ray bursts. The underlying mechanism remains an active area of research. The cycle of stellar birth and death continues across galaxies. Massive stars form from dense molecular clouds and return enriched material to space. Their lifespans are brief on cosmic scales. Through steady physical processes, they contribute to the ongoing transformation of matter in the universe. In the final moments of a massive star's life, the iron core grows steadily heavier. Fusion can no longer provide outward pressure. Gravity draws matter inward with quiet persistence. The core contracts and heats, yet no new energy source appears. The balance that lasted millions of years gives way to a brief, decisive inward motion. As the core compresses, electrons and protons combine to form neutrons and neutrinos. This process reduces electron pressure, which once helped support the core. Neutrinos escape almost freely, carrying energy outward. The density rises rapidly, approaching values found in atomic nuclei. Matter becomes tightly packed in a small central region. The inward collapse continues until neutron degeneracy pressure resists further compression. At this point, the core stiffens abruptly. Infalling material meets this dense surface and slows. The sudden deceleration creates a shock wave that begins moving outward through the surrounding layers of the star. Initially, the shock wave loses energy as it passes through dense material. It must break apart heavy nuclei and push against infalling gas. Neutrinos streaming from the core deposit a small fraction of their energy behind the shock. This additional energy helps revive and sustain the outward motion. Once strengthened, the shock wave travels through the star's outer shells. Layers that once quietly fused lighter elements are lifted and accelerated. The material expands into space, carrying with it elements forged during the star's lifetime. Light begins to emerge from the expanding surface. During this event, neutrinos carry away most of the gravitational energy released in collapse. For a brief period, the star emits an immense number of these nearly massless particles. Though difficult to detect, they provide a clear signal of core collapse. Their passage is swift and largely unhindered. The expanding outer layers form a luminous envelope. As the material moves outward, it cools gradually. Radiation diffuses through the gas, creating a bright but temporary display. The brightness declines over weeks to months, following patterns shaped by radioactive decay within the debris. Nickel and cobalt isotopes produced during the explosion decay into iron. Their decay releases energy that maintains the glow of the expanding remnant. This steady input of energy shapes the light curve observed from distant galaxies. The process follows well-understood nuclear pathways. Inside the remnant core, conditions settle into a new equilibrium. If the mass is suitable, a neutron star remains. It may spin rapidly and possess a strong magnetic field. Surrounding material can form a thin disk before dispersing. Over time, the system becomes quieter and more stable. If the core mass exceeds the supportable limit, collapse continues beyond neutron density. A black hole forms at the center. Material falling inward may briefly form an accretion disk. Some energy can be released along rotational axes. The outer layers, however, continue expanding into space. The geometry of the explosion is not always perfectly symmetrical. Instabilities within the collapsing core can create uneven flows. Convection and turbulence influence how energy is distributed. These variations affect the motion of the remnant core and the shape of the expanding cloud. Shock heating during the explosion raises temperatures in the outer layers. Under these conditions, rapid neutron capture can occur. Heavy elements form in fractions of a second. These nuclei become part of the ejecta, later mixing with interstellar gas over long timescales. As the debris expands, it sweeps up surrounding interstellar material. A shock front forms at the boundary between ejecta and ambient gas. This interaction slows the expansion gradually. The remnant may remain visible for thousands of years as a faint, structured cloud. The light from a core collapse supernova can briefly outshine an entire galaxy. This brightness results from the conversion of gravitational energy into radiation. Despite its intensity, the process follows established physical principles. After the peak, luminosity decreases in a steady and measurable way. Observations across different wavelengths reveal details of the event. Radio waves trace interactions with surrounding gas. X-rays show hot plasma heated by shocks. Optical light reveals expanding layers and elemental composition. Each signal offers a calm record of underlying physical processes. Computer simulations help scientists understand the complex dynamics of collapse. They model neutrino transport, fluid motion, and nuclear reactions. These calculations require significant computational resources. Gradually, they refine our understanding of how shock revival occurs. Gravitational waves may also be produced during asymmetric collapse. These ripples in spacetime travel outward at the speed of light. Their detection provides insight into the inner motion of the core. The signals are subtle and require sensitive instruments to observe. Over centuries, the supernova remnant expands and thins. Magnetic fields shape its structure. Filaments and shells become visible as density varies. Eventually, the remnant merges with the surrounding medium. Its distinct boundary fades into the broader galaxy. Core collapse events contribute to galactic chemical evolution. The expelled elements enrich future generations of stars. Without such events, many heavy elements would remain scarce. The cycle proceeds slowly across cosmic time, linking stellar death to new formation. In distant galaxies, core collapse supernovae serve as markers of ongoing star formation. They occur where massive stars have recently formed and aged. Each event is a brief phase in a long stellar life. After the light fades, space returns to its usual quiet state. When the core of a very massive star collapses beyond the support of neutron pressure, gravity continues its inward work. Matter compresses to densities that cannot be stabilized by known forces. The region becomes smaller and more compact. Space around it curves more strongly. A boundary forms where escape velocity exceeds the speed of light. This boundary is called the event horizon. It is not a surface in the usual sense, but a limit in spacetime. Once matter or light crosses it, returning outward becomes impossible. To a distant observer, infalling material appears to slow and fade near this edge due to gravitational time dilation. Inside the event horizon, the equations of general relativity predict continued collapse. The mass is thought to compress toward a region of extremely high density. The exact nature of this inner state is not fully understood. Current theories suggest a singularity, though quantum gravity may modify this description. During formation, surrounding material may not fall directly inward. If the collapsing star is rotating, angular momentum causes some matter to form an accretion disk. Gas in this disk orbits rapidly and heats through friction. Energy is radiated away gradually as the material spirals closer to the horizon. Magnetic fields within the accretion disk can channel part of the inflowing material into narrow jets. These jets may extend far beyond the original star. They carry energy and particles outward along the rotational axis. The mechanism involves complex interactions between gravity, rotation, and electromagnetic forces. From a distance, the newborn black hole is defined only by mass, spin, and electric charge. These quantities determine its external gravitational field. Other details of the original star are no longer visible. This simplification is sometimes described as the loss of distinguishing features beyond these basic parameters. The formation process releases significant energy, primarily through neutrinos and radiation from the accretion disk. Most of the gravitational energy remains locked within the black hole's mass. The surrounding environment, however, may remain luminous for some time before settling into a quieter state. If the collapsing core has little rotation, accretion may be brief. Much of the outer envelope could have already been expelled. In such cases, the black hole forms with limited additional emission. The region gradually becomes darker as remaining material disperses. Time behaves differently near a black hole. Strong gravity slows clocks relative to distant observers. Light climbing away from the horizon loses energy and becomes redshifted. These effects are predicted by general relativity and confirmed through observations of compact objects in space. The size of the event horizon depends on mass. For a stellar mass black hole, it may span only a few kilometers. Despite this modest radius, the mass can exceed several times that of the Sun. The compactness leads to intense curvature of spacetime in its vicinity. Matter approaching the horizon experiences increasing tidal forces. Differences in gravitational pull between near and far sides stretch objects along the direction of motion. For smaller black holes, this effect becomes significant well outside the horizon. For larger ones, it may occur closer to the boundary. In binary systems, a newly formed black hole may remain gravitationally bound to a companion star. Gas from the companion can transfer into an accretion disk. X-rays are often emitted from the heated inner disk. Over time, the rate of accretion can vary with orbital conditions. Gravitational waves may accompany the final stages of asymmetric collapse. These waves carry information about mass distribution and rotation. They travel outward without significant absorption. Sensitive detectors can record their subtle influence as they pass through Earth. The surrounding interstellar medium responds to the change in mass distribution. If the progenitor star lost material during a supernova, expanding gas continues outward. The black hole remains at the center of this dispersing cloud, largely invisible except for its gravitational influence. Quantum theory predicts that black holes emit very faint radiation known as Hawking radiation. For stellar mass black holes, this emission is extremely weak. The process would take far longer than the current age of the universe to significantly reduce their mass. Over long timescales, black holes may merge with others. If two massive stars formed in a binary system and both collapsed, their remnants can orbit each other. Gradual emission of gravitational waves reduces their separation. Eventually, they coalesce into a single, more massive black hole. The spin of a black hole reflects the angular momentum of its progenitor. Rapid rotation influences the structure of spacetime nearby. It can allow the event horizon to become slightly flattened at the poles. Rotation also affects how efficiently energy can be extracted from the accretion disk. Observational evidence for stellar mass black holes often comes from motion of nearby stars. When a visible star orbits an unseen companion with high mass, calculations can reveal the presence of a compact object. If the mass exceeds neutron star limits, a black hole is inferred. The birth of a black hole marks a transition rather than an end. Matter has shifted into a state governed strongly by gravity. Surrounding space continues its gradual evolution. Gas cools, radiation fades, and the new object becomes part of the galaxy's quiet structure. Across cosmic time, many black holes form from massive stars. They drift within galaxies, sometimes isolated, sometimes in systems. Their presence shapes stellar orbits and influences gas flows. Though invisible directly, their steady gravitational effect remains woven into the broader pattern of the universe. A black hole is a region of spacetime where gravity becomes extremely strong. It forms when enough mass is compressed into a small volume. According to general relativity, mass curves spacetime, and this curvature guides the motion of matter and light. In a black hole, the curvature becomes so deep that certain paths lead only inward. The defining feature of a black hole is the event horizon. This boundary marks the distance at which escape velocity equals the speed of light. Beyond it, all paths through spacetime curve toward the center. The event horizon is not solid. It has no surface you could touch. It is a limit defined by geometry. Outside the event horizon, gravity behaves in a familiar way. A black hole with the same mass as the Sun would attract objects just as the Sun does at the same distance. The difference appears only when matter approaches very close. Near the horizon, spacetime curvature increases steadily. At the center, current equations predict a singularity. This term describes a point where density and curvature become extremely large. It signals that general relativity reaches its limits. Many physicists expect that a future theory combining gravity and quantum mechanics will offer a clearer description. Black holes are described by only a few measurable properties. Mass determines the strength of gravity. Spin describes how quickly the black hole rotates. Electric charge is theoretically possible, though astrophysical black holes likely have very little. These simple parameters fully define the external gravitational field. Light traveling near a black hole follows curved paths. This bending can produce gravitational lensing. Distant stars may appear distorted or multiplied when their light passes close by. The effect has been observed around massive compact objects, confirming predictions of general relativity. Time passes differently near a black hole. Clocks closer to the horizon tick more slowly compared to distant clocks. This gravitational time dilation has been measured in weaker gravitational fields and matches theoretical expectations. Near a black hole, the effect becomes much more pronounced. A black hole does not act as a cosmic vacuum cleaner. Objects must come very close to be captured. At larger distances, orbits can remain stable. Many stars orbit the supermassive black hole at the center of the Milky Way without being drawn inward. When matter falls toward a black hole, it often forms an accretion disk. Friction and compression heat the gas, causing it to emit radiation. The black hole itself does not emit this light. The glow comes from the surrounding material as it loses energy and angular momentum. The size of a black hole's event horizon depends on its mass. For stellar mass black holes, the radius may be only a few kilometers. For supermassive black holes in galactic centers, the horizon can span millions of kilometers. The relationship between mass and radius is direct and predictable. Black holes can rotate. A rotating black hole drags spacetime around it, an effect known as frame dragging. This influences the motion of nearby matter. The region outside the event horizon where dragging is unavoidable is called the ergosphere. Quantum theory suggests that black holes are not completely black. They emit a faint radiation due to quantum effects near the horizon. This Hawking radiation is extremely weak for large black holes. Over immense timescales, it would cause gradual mass loss. Observations of stars orbiting unseen massive objects provide strong evidence for black holes. In the center of our galaxy, stars move in tight, fast orbits around a compact mass. The density required cannot be explained by any known cluster of normal objects. Black holes can merge when two orbit each other closely. As they spiral inward, they emit gravitational waves. These waves carry energy away, reducing the separation. Detectors on Earth have recorded such signals, confirming that black holes exist and behave as predicted. Despite their name, black holes are not holes in space. They are regions where spacetime geometry takes on a particular form. Nothing falls into a separate dimension. Instead, paths through spacetime converge inward once the horizon is crossed. From far away, a black hole appears simple. It influences nearby objects through gravity. It can be surrounded by glowing gas or remain nearly invisible. Its presence is inferred by motion and radiation, not by direct sight of a surface. Inside the event horizon, all possible future paths lead inward. This is a geometric statement rather than a force pulling in a particular direction. The structure of spacetime itself guides motion. Outside observers cannot receive information from within this region. Supermassive black holes reside at the centers of most large galaxies. Their masses range from millions to billions of times that of the Sun. They likely formed through growth and mergers over cosmic time. Their gravitational influence shapes the inner regions of galaxies. Black holes obey the same physical laws as other objects. They conserve energy, momentum, and angular momentum. Their thermodynamic properties, such as entropy and temperature, can be defined mathematically. These relationships link gravity with quantum principles. In essence, a black hole is a prediction of general relativity confirmed by observation. It is not an anomaly but a natural outcome when mass is concentrated beyond a certain limit. Its behavior follows consistent rules, expressed through the curvature of spacetime and the steady influence of gravity. The event horizon is the defining boundary of a black hole. It marks the distance from the center where escape velocity equals the speed of light. Beyond this limit, all possible paths through spacetime lead inward. It is not made of matter. It has no thickness. It is a surface defined entirely by gravity and geometry. From far away, the event horizon appears as a dark sphere. Its size depends only on the mass of the black hole. For a non-rotating black hole, the radius can be calculated directly from mass. This radius is called the Schwarzschild radius. It sets the scale of the horizon. Nothing unusual is felt exactly at the event horizon, at least for a sufficiently large black hole. An observer falling inward would not notice a sharp boundary. The laws of physics remain locally consistent. The horizon is a global feature of spacetime, not a physical shell. Light emitted just outside the horizon can still escape, though it loses energy as it climbs away. This loss appears as gravitational redshift. The closer the light originates to the horizon, the more stretched its wavelength becomes. To distant observers, it fades gradually. As an object approaches the horizon, time dilation becomes increasingly noticeable to distant viewers. Clocks near the boundary appear to tick more slowly. Signals sent outward take longer to arrive. From far away, the object seems to slow and dim, never quite crossing the horizon. For the infalling observer, however, crossing the event horizon happens in finite proper time. Their own clock continues normally. The difference arises from how spacetime is curved. Observers in different positions experience time differently according to general relativity. The event horizon is a one-way boundary. Paths that lead outward no longer exist once crossed. This does not require a force pulling inward. Instead, the geometry of spacetime is arranged so that all future directed paths converge toward the center. In rotating black holes, The horizon still exists, but its shape is slightly altered. Rotation reduces the radius compared to a non-rotating case of equal mass. The mathematics describing this geometry is given by the Kerr solution to Einstein's equations. Just outside the horizon of a rotating black hole lies the ergosphere. In this region, spacetime itself is dragged along by rotation. Objects cannot remain stationary relative to distant stars. Yet the event horizon remains the true boundary beyond which escape is impossible. The surface area of the event horizon is proportional to the square of its radius. In black hole thermodynamics, this area is linked to entropy. The relationship suggests that information about matter falling in may be encoded in subtle ways on the horizon's geometry. Quantum theory predicts small fluctuations near the event horizon. Pairs of virtual particles can form briefly. In certain interpretations, one particle may escape while the other falls inward. This process leads to Hawking radiation, giving the horizon a faint effective temperature. The temperature associated with an event horizon is extremely low for large black holes. A stellar mass black hole would be colder than the cosmic microwave background. As a result, it absorbs more radiation than it emits under current cosmic conditions. If two black holes merge, their event horizons combine into a larger single horizon. The total area after merging is greater than or equal to the sum of the original areas. This property resembles the second law of thermodynamics and supports the concept of horizon entropy. The event horizon does not reflect light like a mirror. Instead, light that crosses it simply continues inward along curved paths. From the outside, no information returns. This absence defines the black hole's darkness. Mathematically, the event horizon is defined by the behavior of light cones in spacetime diagrams. Near the horizon, the cones tilt inward. At the boundary, outward pointing directions become parallel to the surface. Inside, all directions point toward decreasing radius. In dynamic situations, such as during collapse, the location of the event horizon can change. It forms before the collapsing matter reaches the final singular state. Its position depends on the entire future development of spacetime, making it a subtle concept. Astronomical observations of black hole shadows relate to the event horizon. The shadow is slightly larger than the horizon itself. It results from strong light bending near the boundary. Images from radio telescopes provide indirect confirmation of its size. For an observer hovering just above the horizon, enormous acceleration would be required to remain stationary. The closer to the boundary, the greater the needed force. At the horizon itself, remaining fixed relative to distant observers becomes impossible. Despite its abstract nature, the event horizon follows precise equations. It is a prediction of general relativity supported by many lines of evidence. Its existence represents a limit in spacetime, where gravity shapes the possible paths of matter and light. In quiet mathematical terms, the event horizon is a surface beyond which events cannot influence distant regions. It separates what can communicate with the wider universe from what cannot. Within this boundary, spacetime continues, guided by the same underlying laws. Spacetime curvature is the central idea of general relativity. Instead of viewing gravity as a force, the theory describes mass and energy as shaping the geometry of spacetime. Objects then follow paths within this curved geometry. What we perceive as gravitational attraction is the natural motion along these curved paths. In flat spacetime, such as far from massive objects, light travels in straight lines. Clocks tick at steady rates relative to one another. When mass is present, spacetime bends. Light follows curved trajectories, and clocks at different positions measure time at slightly different rates. The curvature created by Earth is gentle but measurable. Satellites orbit because they follow the curved geometry around our planet. Their paths are not driven by a pulling force in the traditional sense. Instead, they move along geodesics, which are the straightest possible paths in curved spacetime. Massive objects create deeper curvature. The sun's mass bends spacetime enough to affect the motion of planets and the path of light from distant stars. During a solar eclipse, this bending can be observed as a small shift in star positions, confirming theoretical predictions. Spacetime combines 3 dimensions of space with one of time into a unified structure. Curvature can involve both spatial bending and changes in time flow. Near a massive body, time passes more slowly compared to distant regions. This effect has been measured using precise atomic clocks. The equations describing spacetime curvature are expressed in Einstein's field equations. These relate the distribution of mass and energy to the geometry of spacetime. Though mathematically complex, the principle is simple. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. In regions with extremely strong gravity, such as near neutron stars or black holes, curvature becomes pronounced. Light can orbit or be significantly deflected. The geometry shapes possible paths so strongly that escape may no longer be possible within certain boundaries. Gravitational lensing is a visible consequence of spacetime curvature. Light from distant galaxies bends as it passes near massive clusters. This bending can create arcs or multiple images. The pattern of distortion provides information about both visible and invisible mass. Spacetime curvature is not limited to static objects. Moving masses can create changes that propagate outward as gravitational waves. These waves are ripples in the curvature itself. They travel at the speed of light and have been detected from merging black holes. Even small amounts of mass contribute to curvature. Every planet, star, and particle plays a role. The effect from a single object may be tiny, but collectively these influences shape the large-scale structure of the universe. In everyday life, curvature is too slight to notice directly. Objects fall because they follow curved paths near Earth. To human perception, this appears as a force pulling downward. General relativity offers a deeper geometric explanation. The curvature of spacetime also affects the passage of time on Earth. Clocks at higher altitudes tick slightly faster than those at sea level. Global positioning systems must account for this difference to maintain accuracy. These adjustments confirm the practical reality of curved spacetime. In empty regions far from mass, spacetime approaches a flat condition. Yet even there, the expansion of the universe influences its geometry. On cosmic scales, curvature is tied to the overall density of matter and energy. Black holes represent regions where curvature becomes extreme. The geometry near their centers is predicted to grow without bound. This signals the limits of current theory and suggests that quantum effects may become important. The concept of geodesics helps describe motion in curved spacetime. A geodesic is the path that requires no force in the local frame. Planets orbiting stars follow geodesics determined by the star's mass. Their motion appears curved because spacetime itself is curved. Curvature can be visualized with simple analogies, such as a stretched fabric bending under weight. Though incomplete, this image helps convey how mass changes geometry. The true mathematics operates in 4 dimensions, beyond direct visualization. Spacetime curvature influences not only motion but also the flow of energy and radiation. Light climbing out of a gravitational well loses energy and becomes redshifted. This shift is another measurable consequence of curved geometry. In cosmology, spacetime curvature determines the universe's overall shape. If density were high enough, space could be positively curved. Current observations suggest near flatness on large scales, with only slight deviations. The presence of dark matter is inferred partly through its gravitational effects. Though invisible, it contributes to curvature. Galaxies rotate and clusters bend light in ways that require additional mass shaping spacetime. Spacetime curvature offers a unified description of gravity. It replaces the idea of a pulling force with a geometric framework. Through careful observation and measurement, this curvature reveals itself in subtle but consistent ways across the universe. An accretion disk forms when gas and dust move toward a massive object but possess angular momentum. Instead of falling directly inward, the material spreads into a rotating disk. Gravity pulls it closer, while rotation keeps it in orbit. The balance between inward attraction and sideways motion shapes a thin, flattened structure. Within the disk, particles follow nearly circular paths. Friction and small collisions cause energy to be redistributed. As energy is lost through radiation, matter gradually spirals inward. The process is steady and governed by conservation of angular momentum. Over time, material drifts closer to the central mass. Accretion disks can surround black holes, neutron stars, or young forming stars. In each case, the underlying physics is similar. Gravity draws matter inward, while rotation organizes it into a disk. The details depend on mass, temperature, and magnetic fields present in the environment. As gas moves inward, gravitational potential energy converts into heat. The inner regions of the disk become hotter than the outer parts. Temperatures can rise high enough to emit visible light, ultraviolet radiation, or even X-rays near compact objects. The glow comes from heated gas, not from the central body itself. Viscosity within the disk plays an important role. Though the gas is thin, magnetic turbulence can create effective friction. This allows angular momentum to move outward while mass moves inward. Without this transport mechanism, accretion would proceed much more slowly. The thickness of an accretion disk depends on temperature and pressure. Cooler disks tend to be thin and flat. Hotter disks may puff up slightly, becoming thicker. Radiation pressure can also influence the vertical structure in especially luminous systems. In disks around young stars, dust grains collide and stick together. Over time, these grains can grow into larger bodies. This gradual accumulation may lead to planet formation. The disk provides both the material and the organized rotation needed for this process. Near a black hole, the inner edge of the accretion disk is set by stable orbital limits. Inside a certain radius, circular orbits are no longer possible. Material crossing this boundary quickly moves toward the event horizon. The disk's inner edge reflects the geometry of spacetime. Accretion disks often display spiral density waves. These are regions where gas becomes slightly denser as it orbits. The waves help redistribute angular momentum and can influence the overall evolution of the disk structure. Magnetic fields thread through many accretion disks. As the disk rotates, these fields can twist and amplify. Magnetic forces contribute to turbulence and may help launch narrow jets along the rotational axis of the central object. The rate at which matter flows through a disk is called the accretion rate. Higher rates lead to greater luminosity. In some systems, the rate changes over time, producing variations in brightness. These changes can occur gradually or in repeating cycles. Radiation from an accretion disk carries away energy. This outward flow of light allows matter to settle into tighter orbits. The balance between gravitational pull and radiation pressure determines how bright the disk can become. In binary star systems, one star can transfer material to its companion. If the companion is a compact object, the transferred gas forms an accretion disk. The disk may emit strongly in X-rays, providing evidence of the unseen central mass. Accretion disks are not perfectly smooth. Instabilities can develop as density and temperature vary. These instabilities may cause fluctuations in brightness. Despite such variations, the overall structure remains governed by steady physical principles. The color of light from a disk depends on temperature distribution. Outer regions emit cooler, redder light. Inner regions emit bluer or more energetic radiation. The combined spectrum reveals information about disk size and mass flow. Over long timescales, an accretion disk can change shape as material is consumed. If supply from surrounding gas declines, the disk thins and dims. Eventually, it may disperse almost entirely, leaving only faint traces. The motion within a disk follows Keplerian rotation in many cases. This means orbital speed decreases with distance from the center. The predictable pattern allows astronomers to estimate the mass of the central object by observing disk motion. In active galactic nuclei, supermassive black holes are fed by large accretion disks. These disks can span vast distances and emit across the electromagnetic spectrum. Their steady radiation marks regions where gravity shapes luminous structures. Cooling processes within the disk affect its stability. Radiation, convection, and sometimes outflows help regulate temperature. The interplay of heating and cooling maintains a dynamic but balanced system over extended periods. Accretion disks represent an orderly response to gravity and motion. Matter does not simply fall inward. Instead, it organizes into rotating layers, gradually giving up energy. Through this measured process, mass transfers inward while light flows outward into surrounding space. Black holes are often imagined as objects that pull in everything around them. In reality, their gravity follows the same rules as any other mass. If the Sun were replaced by a black hole of equal mass, Earth would continue orbiting at the same distance. The gravitational influence at that range would remain unchanged. Gravity weakens with distance according to an inverse square law. Far from a black hole, its pull is no stronger than that of any other object with the same mass. Objects must come relatively close before the effects become significant. Most stars in a galaxy remain far beyond this region. A black hole does not actively search for matter. It does not generate suction. Matter must already be on a path that brings it near the event horizon. Otherwise, it can orbit stably for long periods, just as planets orbit stars. In galaxies, stars move under the combined gravity of billions of other stars, gas, and dark matter. The central supermassive black hole influences only the inner region strongly. Beyond that, its effect blends with the overall gravitational field of the galaxy. For an object to be captured, it must lose enough energy to cross the event horizon. Simply passing nearby is not enough. Many objects follow curved trajectories and continue outward again, especially if they approach at high speed. Accretion requires a supply of gas that can shed angular momentum. Without this process, material cannot spiral inward. In many regions of space, gas density is extremely low. As a result, accretion onto isolated black holes can be minimal. Binary systems provide clearer examples. When a black hole orbits a companion star, matter can transfer through gravitational interaction. Even then, the process is gradual. The companion is not instantly consumed. Mass loss occurs over extended timescales. Tidal forces near a black hole can disrupt objects that pass too closely. Yet, this requires proximity within a certain radius. At larger distances, the difference in gravitational pull across an object is small and manageable. The idea of a vacuum cleaner suggests constant inward flow. In space, motion depends on initial velocity and direction. Objects in stable orbit have no reason to fall inward unless disturbed by another force or collision. Even light must approach within the event horizon to be trapped permanently. Photons passing at greater distances are merely deflected. This bending can be measured as gravitational lensing, but it does not imply unlimited capture. Supermassive black holes at galactic centers coexist with dense star clusters. Many stars orbit for billions of years without falling in. Their motion reflects balanced gravitational forces, not unavoidable collapse. Gas clouds near a black hole can form accretion disks, but only if conditions allow angular momentum to be redistributed. In sparse regions, little material reaches the center. The black hole remains largely inactive. The growth of black holes over cosmic time depends on available matter. Some grow rapidly in early galaxies where gas is abundant. Others remain relatively quiet when supply is limited. Their behavior reflects environment, not inherent appetite. Gravitational influence has no special reach beyond what mass dictates. A black hole with the mass of Earth would exert Earth's gravity. Only its compactness would differ, affecting conditions very close to its surface. Space itself is vast and mostly empty. The chance of random objects wandering directly into a black hole is small. Motion in galaxies follows predictable orbital patterns shaped by large-scale mass distribution. When stars pass near a supermassive black hole, their orbits can change slightly. Yet complete capture requires specific conditions. Many stars approach, curve around, and move away again along altered paths. The event horizon defines the point of no return. Outside this boundary, escape remains possible. The region where capture is certain is small compared to the size of a galaxy. Computer simulations of galactic dynamics show stable structures over billions of years. Black holes contribute to these structures without dominating them entirely. Their presence is significant but not overwhelming. Matter falling into a black hole often emits radiation before crossing the horizon. This radiation can even push back on inflowing gas. In some cases, outward pressure limits how fast accretion proceeds. Black holes are compact concentrations of mass. Their gravity is powerful nearby, yet ordinary at distance. They do not sweep through space collecting everything. Instead, they participate quietly in the broader gravitational balance of the universe. Black holes can be grouped by mass into different categories. Stellar mass black holes form from the collapse of massive stars. Their masses typically range from a few to several dozen times that of the Sun's supermassive black holes. By contrast, contain millions to billions of solar masses and reside in the centers of galaxies. A stellar mass black hole is compact, with an event horizon only a few kilometers wide. Despite this small size, its gravity near the horizon is intense. A supermassive black hole has a far larger horizon, sometimes comparable to the orbit of a planet, yet its average density can be surprisingly low. The origins of these two types differ. Stellar mass black holes result from core collapse in dying stars. Supermassive black holes likely grow over long periods through accretion of gas and mergers with other black holes. Their formation history is linked closely to galactic evolution. Stellar mass black holes are often found in binary systems. They may orbit a companion star and draw matter from it. This accretion can produce X-rays that reveal their presence. Supermassive black holes, however, sit at galactic centers and influence large regions of surrounding space. The gravitational reach of a stellar mass black hole is limited. The strong effects are confined to nearby space. A supermassive black hole shapes the motion of stars within the central light years of its galaxy. Farther out, the combined mass of stars and dark matter becomes more important. Time dilation occurs near both types of black holes. Close to the event horizon, clocks run more slowly relative to distant observers. The effect depends on proximity to the horizon rather than overall mass, though larger horizons allow gentler tidal forces at the boundary. Tidal forces differ significantly between the two. Near a small stellar mass black hole, differences in gravity across a short distance can be extreme. Near a supermassive black hole, those differences at the horizon may be much weaker, allowing objects to cross with less immediate distortion. Accretion disks form around both types when gas is available. In stellar systems, the disk may be fed by a companion star. In galaxies, supermassive black holes can gather gas from interstellar clouds. The disks differ in scale but follow similar physical principles. Supermassive black holes can power active galactic nuclei. When accretion rates are high, they emit enormous amounts of radiation. Stellar mass black holes can also be luminous, though on a much smaller scale, often observed as X-ray binaries. The growth rate of stellar mass black holes is usually modest. They gain mass gradually from companions or occasional mergers. Supermassive black holes can grow substantially over cosmic time, especially during periods of abundant gas in young galaxies. Observational methods vary. Stellar mass black holes are detected through their influence on nearby stars or emitted X-rays. Supermassive black holes are studied by tracking star orbits at galactic centers and by imaging surrounding accretion flows. Gravitational waves provide insight into both categories. Mergers of stellar mass black holes have been detected by ground-based observatories. Mergers of supermassive black holes are expected to produce lower frequency waves, observable with future space-based detectors. Despite their size difference, both types obey the same fundamental equations of general relativity. Their event horizons are described by similar mathematical solutions. The scaling changes, but the underlying geometry remains consistent. The relationship between galaxies and their central supermassive black holes appears systematic. The mass of the black hole often correlates with properties of the galaxy's central bulge. This suggests a shared evolutionary history over billions of years. Stellar mass black holes are more numerous. They form wherever massive stars end their lives. Supermassive black holes are rarer, typically one per large galaxy. Their presence, however, has broad structural consequences. In terms of density, a stellar mass black hole is far denser on average than a supermassive one. As mass increases, the radius grows proportionally, lowering average density. This counterintuitive result follows directly from the equations defining the horizon. The environments around these black holes also differ. Stellar mass black holes inhabit star clusters or binary systems. Supermassive black holes reside in dense galactic nuclei, surrounded by stars, gas, and sometimes dust tori. Jets can emerge from both types when magnetic fields and rotation align properly. In stellar systems, jets may extend light years. In galactic centers, jets can span thousands of light years, shaping intergalactic space. The timescales of change vary with size. Variability in stellar mass black hole systems can occur over seconds or hours. For supermassive black holes, similar processes unfold over years or longer due to their larger physical scales. Both stellar mass and supermassive black holes represent natural outcomes of gravitational physics. Their differences arise from mass and environment, yet their core properties remain governed by the same principles of spacetime curvature and energy conservation. At the center of most large galaxies lies a supermassive black hole. Its mass can range from millions to billions of times that of the Sun. Though compact compared to the galaxy itself, it exerts a steady gravitational influence on nearby stars. This central presence is now considered a common feature of galactic structure. In the Milky Way, the central black hole is known as Sagittarius A star. Contains about 4 million solar masses. Stars orbit it in tight, rapid paths, allowing astronomers to calculate its mass with precision. These observations provide strong evidence for a compact and massive object. The influence of a central black hole is strongest within the inner region of a galaxy. Stars close to the center move faster than those farther out. Their orbits trace the curvature of spacetime created by the concentrated mass. Beyond this region, the combined gravity of stars and dark matter dominates. Gas clouds drifting toward the galactic center can form an accretion disk around the black hole. As gas spirals inward, it heats and emits radiation. In some galaxies, this process produces a luminous core known as an active galactic nucleus. When accretion rates are low, the central black hole may appear quiet. It does not emit light directly. Only the motion of surrounding stars reveals its presence. Many galaxies, including the Milky Way, currently host relatively calm central black holes. The mass of a galaxy's central black hole often correlates with the size of its bulge. Larger bulges tend to contain more massive black holes. This relationship suggests that galaxy formation and black hole growth are linked processes over cosmic time. Supermassive black holes may grow through steady accretion of gas and dust. They can also gain mass by merging with other black holes during galactic collisions. Such mergers release gravitational waves and gradually reshape the galactic center. The event horizon of a supermassive black hole is much larger than that of a stellar mass black hole. Despite this size, tidal forces at the horizon can be relatively mild. The scale changes, but the geometry follows the same physical laws. Observations using radio telescopes have produced images of the shadow of central black holes in nearby galaxies. These images match predictions of general relativity. They show a dark region surrounded by glowing gas in orbit. The central black hole can influence star formation in its galaxy. Powerful outflows from active nuclei may heat surrounding gas. This heating can limit how quickly new stars form, subtly shaping the evolution of the galaxy. In the early universe, supermassive black holes appear to have formed quickly. Quasars observed at high redshift indicate rapid growth. The mechanisms that allowed such growth are still studied through simulations and observation. Stars that pass too close to a central black hole can be disrupted by tidal forces. The resulting stream of gas may feed the accretion disk temporarily. These events are rare but observable across large distances. Despite their mass, central black holes occupy a tiny fraction of galactic volume. The galaxy itself spans tens of thousands of light years. The black hole's direct gravitational dominance extends only a few light years outward. The motion of stars near the galactic center provides insight into spacetime curvature. Precise measurements confirm predictions of general relativity. Even subtle effects, such as gravitational redshift, have been detected in stellar spectra. Black holes at galactic centers are not isolated from their surroundings. They exist within dense stellar clusters. Interactions between stars, gas, and the black hole create a dynamic but stable environment over long timescales. The rotation of a supermassive black hole can affect the orientation of its accretion disk and jets. Frame dragging near the horizon influences nearby spacetime. This effect may shape how energy is directed outward. Over billions of years, the growth of central black holes and the assembly of galaxies proceed together. Mergers between galaxies often bring their central black holes into orbit around each other before eventual coalescence. The radiation from active galactic nuclei can be detected across vast distances. It serves as a beacon of early cosmic activity. Yet many central black holes remain dim, quietly shaping stellar orbits without bright emission. The gravitational field near a supermassive black hole provides a natural laboratory for testing theories of gravity. Observations of star motions and light bending refine our understanding of extreme spacetime conditions. At the heart of a galaxy, the central black hole represents a concentrated point of mass within a vast rotating system. It does not control every motion, but it anchors the inner region through steady gravitational presence woven into the broader structure. Gravitational time dilation is a consequence of spacetime curvature described by general relativity. When mass bends spacetime, it affects not only distances but also the flow of time. Clocks placed closer to a massive object tick more slowly compared to clocks farther away. This difference is small near Earth but measurable with precise instruments. The effect arises because gravity alters the geometry through which time progresses. In stronger gravitational fields, the path through spacetime is shaped more deeply. A clock resting near a massive body experiences this curvature directly. From the perspective of a distant observer, its seconds stretch slightly longer. On Earth, gravitational time dilation has been confirmed using atomic clocks at different altitudes. A clock placed on a mountain runs a bit faster than one at sea level. The difference is tiny, yet consistent with predictions. Even satellites in orbit must account for this variation. Global positioning systems rely on accurate time signals from satellites. These satellites orbit higher above Earth's surface, where gravity is weaker. As a result, their clocks tick faster relative to clocks on the ground. Engineers adjust for this shift to maintain precise navigation. Near more massive objects, the effect becomes stronger. Around neutron stars or black holes, time dilation can be significant. A clock close to such an object would appear to slow dramatically when viewed from afar. The closer it approaches the event horizon, the slower it seems to run. For an observer falling toward a black hole, their own clock feels normal. Time passes steadily in their frame. The difference appears only when compared to distant observers. This illustrates how time in relativity depends on position and motion. Light escaping from a strong gravitational field loses energy. Its wavelength stretches, a phenomenon known as gravitational redshift. This shift is closely related to time dilation, since the frequency of light reflects the rate at which time passes at its source. In binary star systems, gravitational time dilation affects signals exchanged between stars. Spectral lines may shift slightly due to differences in gravitational potential. Careful measurements allow astronomers to detect these subtle changes. The mathematics describing gravitational time dilation comes directly from Einstein's field equations. The rate at which time passes depends on the gravitational potential at a given location. The deeper the potential well, the slower the local clock ticks relative to distant space. Gravitational time dilation does not require extreme conditions. Even everyday objects create slight curvature. Every mass contributes, though the effect becomes noticeable only near large bodies. Precision experiments continue to confirm the theory in varied settings. In the vicinity of a black hole, the slowing of time becomes profound. To a distant observer, an object approaching the event horizon appears to slow and fade. Signals from it become increasingly redshifted. The crossing of the horizon is never directly seen from afar. This stretching of time does not imply a breakdown of physics. The laws remain consistent. Differences arise because observers occupy different regions of curved spacetime. Each measures time according to local conditions. Gravitational time dilation also plays a role in cosmology. On large scales, differences in gravitational potential can influence the rate at which time flows in various regions. These variations are small but considered in precise cosmological models. The concept challenges everyday intuition. Time is often assumed to be universal and constant. Relativity shows that time is flexible, shaped by gravity and motion. This flexibility has been demonstrated repeatedly through observation. Experiments using clocks on airplanes have measured combined effects of motion and gravity. These results align with theoretical predictions. Though small, the shifts confirm that time is not identical everywhere. In strong gravitational fields, time dilation affects how processes unfold. Reactions near a compact object appear slower to distant observers. This influences how we interpret signals from extreme environments in space. Gravitational time dilation ensures that energy is conserved in curved spacetime. The redshift of light climbing out of a gravitational well reflects the change in time rate. The relationship maintains consistency within physical laws. The closer two clocks are in gravitational potential, the smaller their difference in ticking rate. Only significant changes in altitude or proximity to massive objects produce noticeable shifts. The gradient of curvature determines the scale of the effect. In everyday life, gravitational time dilation remains subtle, yet it is woven into the structure of spacetime around us. From mountain tops to satellite orbits, the quiet bending of time proceeds continuously. Gravitational time dilation reveals that time is part of the fabric shaped by mass and energy. It flows at different rates depending on location. This variation is steady and predictable, guided by the geometry of spacetime itself. Hawking radiation is a theoretical prediction that black holes are not entirely dark. It arises from the combination of quantum mechanics and general relativity. Near the event horizon, quantum fields are never completely still. Small fluctuations occur naturally, even in empty space. In quantum theory, pairs of virtual particles can briefly appear and disappear. Normally, they recombine almost immediately. Near a black hole's event horizon, the strong curvature of spacetime can separate these pairs before they reunite. One particle may fall inward while the other escapes. To a distant observer, the escaping particle appears as radiation emitted by the black hole. The particle that falls inward effectively carries negative energy relative to the outside universe. This reduces the black hole's total mass slightly over time. The radiation predicted by this process is extremely faint for large black holes. A stellar mass black hole would emit far less energy than it absorbs from the surrounding cosmic background. Its temperature would be only a fraction of a degree above absolute zero. The temperature of Hawking radiation depends inversely on mass. Smaller black holes would be warmer and radiate more strongly. Larger black holes are colder and emit less. This relationship follows directly from the equations combining gravity and quantum effects. Hawking radiation gives black holes a thermodynamic character. They can be assigned a temperature and entropy. The entropy is proportional to the area of the event horizon, not its volume. This idea links gravity with information and quantum theory. Over immense timescales, Hawking radiation would cause a black hole to lose mass gradually. As mass decreases, the temperature would rise. The process accelerates as the black hole becomes smaller, though for stellar mass black holes this would take far longer than the current age of the universe. The radiation spectrum resembles that of a blackbody, meaning it depends mainly on temperature. It does not carry detailed information about the matter that originally formed the black hole. This has led to deep questions about how information is preserved in physical processes. The prediction of Hawking radiation was made in the 1970s by Stephen Hawking. It emerged from calculations involving quantum fields in curved spacetime. The result was surprising because classical physics suggested black holes could only absorb, not emit. Although Hawking radiation has not been directly observed from astrophysical black holes, the theory is widely accepted. The emission is too weak to detect with current instruments. Researchers explore related effects in laboratory analog systems. The concept does not imply that particles are created from nothing in a simple sense. Instead, it reflects how quantum fields behave in strong gravitational environments. Energy conservation remains intact when the full system is considered. Near the event horizon, time and space are curved significantly. Quantum fluctuations respond to this curvature. The separation of particle pairs can be understood as a consequence of how different observers define energy in curved spacetime. If very small black holes existed, they would radiate more noticeably. In theory, primordial black holes formed in the early universe could have masses low enough to evaporate within cosmic time. Searches for their final bursts remain ongoing. Hawking radiation suggests that black holes are not eternal in a strict sense. Given sufficient time, they would gradually shrink and eventually disappear. The timescale for large black holes, however, is almost unimaginably long. The idea also connects gravity to thermodynamics. Black hole temperature, entropy, and radiation form a consistent framework. This relationship hints at deeper principles that may unify fundamental forces. The slow emission of radiation from a black hole is uniform and gentle. It does not resemble an explosion under ordinary conditions. Only in the final stages of evaporation, when the mass becomes very small, would the process accelerate significantly. Mathematically, Hawking radiation arises when quantum field equations are solved near an event horizon. Different observers disagree about the definition of vacuum. This difference leads to the appearance of particle emission at infinity. The concept has inspired research into the nature of spacetime at the smallest scales. It suggests that gravity and quantum theory are linked in ways not yet fully understood. Ongoing studies aim to clarify this connection. Even though the radiation is faint, the prediction is profound. It shows that black holes participate in quantum processes. They are not isolated from the fundamental behavior of fields and particles. Hawking radiation provides a quiet reminder that empty space is not truly empty. Quantum fluctuations persist everywhere. Near a black hole, these subtle effects become significant enough to allow a slow exchange of energy with the wider universe. In the early universe, the first black holes likely formed from the collapse of massive, short-lived stars. These stars contained mostly hydrogen and helium. When their cores failed to support fusion, gravity completed its work. The resulting black holes were modest in mass, yet they marked the beginning of a long process of growth. As galaxies assembled from merging clouds of gas and dark matter, black holes moved with them. Some settled into central regions where gas density was higher. Over time, steady accretion added mass. Each infalling cloud contributed a small increase, measured against the vast timescales of cosmic history. During periods when galaxies were rich in cold gas, central black holes could grow more rapidly. Accretion disks brightened, forming quasars visible across billions of light years. These luminous phases were temporary. When gas supplies thinned, activity subsided and the galaxy's core grew quieter again. Galaxy mergers played an important role in black hole evolution. When two galaxies combined, their central black holes moved toward each other through gravitational interactions. Eventually, they formed a binary system. Gradual emission of gravitational waves brought them closer still. The merger of two black holes released energy in the form of gravitational waves. These ripples traveled outward at the speed of light. After coalescence, a single, more massive black hole remained at the center of the newly formed galaxy. Over billions of years, many supermassive black holes increased their mass through repeated mergers and steady accretion. Their growth was not constant but occurred in episodes. Quiet intervals separated brighter, more active phases. Stellar mass black holes also evolved across cosmic time. They formed wherever massive stars ended their lives. Some remained isolated. Others gained mass from companion stars or through mergers with other compact objects. In dense star clusters, interactions between stars could lead to the formation of intermediate mass black holes. These objects bridge the gap between stellar mass and supermassive scales. Their existence is still studied through observation and simulation. As the universe expanded, the average density of gas decreased. This gradual thinning reduced the overall accretion rate onto many black holes. Over time, luminous quasars became less common than in the early universe. Despite this decline, central black holes continued to shape their host galaxies. Outflows from active nuclei could heat surrounding gas. This heating influenced how quickly new stars formed, subtly guiding galactic evolution. Black holes also drifted through galaxies after mergers. Some may have been displaced slightly from the center due to asymmetries in gravitational wave emission. Most eventually settled back toward the central gravitational well. On the largest scales, black holes contribute to the energy balance of the universe only indirectly. Their influence is local to galaxies. The expansion of space itself proceeds independently of their presence. As cosmic time advances, stellar populations age. Fewer massive stars form in many galaxies. This reduces the rate at which new stellar mass black holes appear. Existing ones persist, orbiting within their galactic environments. Supermassive black holes will continue to merge when galaxies collide in the distant future. Each merger increases mass and alters spin. The resulting gravitational waves carry information about these long processes. In the far future, as star formation slows further, accretion onto black holes will diminish. Many will remain quiet, surrounded by sparse gas. Their gravitational presence will endure even as luminous activity fades. Given enough time, Hawking radiation predicts that black holes slowly lose mass. For supermassive black holes, this process requires durations far beyond the current age of the universe. Their evaporation lies in a distant era. As galaxies drift farther apart due to cosmic expansion, interactions become rarer. Black hole growth through mergers will slow. Isolated systems will evolve more gently, shaped mainly by internal dynamics. Over trillions of years, many stars will fade into compact remnants. Black holes will represent a larger fraction of remaining mass in galaxies. They will orbit within systems that grow progressively dimmer. Even in such distant epochs, gravitational laws remain unchanged. Black holes will continue to curve spacetime around them. Their role shifts gradually, reflecting changes in surrounding matter and radiation. Across cosmic time, black holes evolve through formation, growth, and quiet persistence. They are shaped by the environment of their galaxies and by the steady unfolding of universal expansion. Their story extends calmly across billions of years. Black holes are often associated with extreme events, yet most of the time they exist quietly. Once formed, Many drift through their galaxies without bright accretion disks or visible jets. They do not shine on their own. Their presence is known mainly through the motion of nearby stars and gas. In regions far from dense clouds, a black hole may have little material to draw inward. Without accretion, it emits almost no radiation. It simply curves spacetime around it, shaping orbits in subtle ways. The surrounding stars continue their paths with steady regularity. At the center of many galaxies, supermassive black holes remain calm for long periods. Gas density in these regions can be low. Without a steady inflow of matter, the central object appears dim. Only careful measurements reveal the deep gravitational well at the core. Stellar mass black holes scattered through galaxies are even more difficult to notice. If they are not part of a binary system, they can pass through interstellar space almost invisibly. Their influence extends only across a limited range set by their mass. Gravity from a black hole does not announce itself with sound or light. It operates silently, altering trajectories over long timescales. Stars may orbit for billions of years under its influence without sudden change. The quiet presence of black holes contributes to the stability of galactic centers. They're mass anchors surrounding star clusters. Though compact, they provide a steady gravitational focus within a much larger system. In globular clusters, intermediate mass black holes may reside without dramatic activity. Their detection relies on the collective motion of many stars. The overall appearance of the cluster remains largely unchanged. Even when matter falls inward, much of the process is gradual. Accretion disks can glow, yet once material is consumed, activity subsides. The black hole returns to a quieter state, defined mainly by mass and spin. Across cosmic distances, most black holes are not actively feeding. Bright quasars represent only certain phases in their long histories. For much of their existence, they are dark and steady. The gravitational field around a black hole blends into the wider galactic field. Beyond a certain distance, its effect is indistinguishable from that of any other object with similar mass. Space around it appears ordinary. Black holes do not roam galaxies collecting everything in their path. They follow the same orbital dynamics as other massive bodies. Their motion is governed by the combined gravity of the galaxy as a whole. When two black holes orbit each other quietly before merging, they may do so over millions of years. Only near the end do gravitational waves become strong. For most of that time, their presence is subtle. The fabric of spacetime curves around each black hole in a precise way. This curvature persists whether or not matter is nearby. It is a constant geometric feature, requiring no visible activity. In intergalactic space, if black holes exist there, they would be nearly impossible to detect. With little surrounding matter, they would not emit radiation. Only gravitational lensing might reveal their position. Black holes also serve as long-term repositories of mass. Matter that crosses the event horizon remains hidden from the wider universe. Yet the overall gravitational influence continues unchanged. The quiet presence of black holes reminds us that much of the universe operates without spectacle. Processes unfold over immense spans of time. Activity alternates with calm in measured cycles. In computer simulations of galaxy formation, black holes appear as stable components. They grow, merge, and then settle. The majority of their existence is marked by equilibrium rather than rapid change. Even near a black hole, stable orbits can persist. Stars may circle at safe distances indefinitely. The system can appear balanced and orderly, despite the extreme curvature closer in. The universe contains countless black holes formed from stellar evolution. Most remain undetected, woven into the broader pattern of galaxies. Their role is steady rather than dramatic. In the vastness of space, black holes represent concentrated points of mass. They do not dominate every scene. Instead, they exist quietly within the cosmic landscape, shaping motion through gravity while remaining largely unseen.